all around us, there are these powerful, totally unseen forces at work. I mean, they're inflating our tires, they're powering our engines, they even shape our weather. I'm talking about gases. And while they seem completely chaotic and random, they're actually governed by a beautifully simple set of rules. And today, we're going to uncover those rules.
So check this thing out. This strange-looking device is called an aeolipile. It was described almost 2,000 years ago, and it's one of humanity's very first steam engines. The idea is simple. You heat the water, it turns to steam, a gas, which then rushes out of these nozzles, making the whole sphere spin. It's a brilliant, really early example of turning the power of an expanding, invisible gas into actual physical motion. But it also brings up a fantastic question.
How can you build engines, or predict the weather, or design any of the thousands of modern technologies we rely on using a substance that's fundamentally invisible and just seems like pure chaos? Well, that is the core mystery we're going to unravel today. To answer that, we first need a new way of thinking about it, a new mental model. We've got to stop picturing a gas as just, well, empty air, and start seeing what it's actually made of on a microscopic level. I want you to imagine a sealed box, and it's filled with trillions of super fast, super tiny billiard balls, all just ricocheting off each other and the walls at incredible speeds. Now, this isn't just a fun little analogy, it's pretty much what a gas actually is, a huge swarm of molecules in constant, chaotic motion. The great physicist James Clerk Maxwell came up with a famous thought experiment to help us get our heads around this chaos. He imagined a tiny being. He called it a demon, who was fast enough and sharp-eyed enough to see and interact with every single one of those bouncing particles.
So Maxwell pictured this demon guarding a tiny little door between two chambers of gas. When a fast-moving, high-energy particle comes zipping along, the demon opens the door and lets it into one chamber. When a slow-moving, low-energy particle moseys on by, he lets it into the other one. Just by sorting the molecules by speed, the demon would actually make one side hot and the other side cold, all without doing any real work itself.
And this is the brilliant insight from Maxwell's little thought experiment. It reveals what temperature actually is. See, it's not some abstract property. It's simply a measure of the average speed, the average kinetic energy of all those bouncing molecules in a system. Hot just means fast particles. Cold means slow particles. It's really that simple.
So, once we start picturing a gas as a bunch of bouncing particles and temperature as just their average speed, we can begin to find simple, predictable rules inside all that chaos. Let's take a look. We're going to focus on three key things here. Three variables. First up is pressure. We'll call it P. That's just the combined force of all those tiny particles constantly smacking into the walls of their container. Next is volume, or V, which is simply the amount of space the gas is taking up. And finally, temperature, T, which as we just learned is really just the average speed of those particles.
Okay, now let's start connecting them. Imagine you take a balloon and you squeeze it. You're decreasing its volume, right? The gas particles inside now have way less room to move, so they're going to hit the walls of that balloon much more often. More frequent collisions means a greater force on the walls. In other words, you get higher pressure.
And just like that, you've stumbled onto our first rule, which was discovered by Robert Boyle. It's called Boyle's Law. If you keep the temperature the same, pressure and volume are basically opposites. Squeeze the volume down, the pressure goes up. Let the volume expand, the pressure goes down.
Okay, so what if we heat the gas instead? This increases the temperature, which means our little particles start moving a whole lot faster. They hit the walls of their container harder and more often, and they push outwards with more force. Now, if the container is flexible, like a hot air balloon, this outward push causes the gas to expand to a larger volume. And this relationship is known as Charles' law. If you keep the pressure constant, the volume and temperature move together. As you increase the temperature, the volume increases right along with it. This is the very principle that makes hot air balloons fly. So here's the really crucial part. These individual rules, Boyle's law and Charles' law, they can actually be combined into one single, incredibly powerful equation, the ideal gas law. It says that pressure times volume is proportional to the number of particles, that's N, and their temperature. That R is just a special number we need to make the units work out. But the core idea is simple. This one single formula connects pressure, volume, and temperature in one beautiful, elegant package.
Now, this isn't just some neat piece of physics theory you find in a textbook. No way. This equation is one of the absolute cornerstones of modern engineering.
Understanding it is what allows us to build machines that power our entire world.
Seriously, every time you fly in a jet or drive a car or even just flip a light switch that's powered by a power plant, you're seeing the ideal gas law in action. From rocket engines to the cylinders in your car, they all work by mastering that relationship between the pressure, volume, and temperature of a gas.
Let's just look at a simple piston engine. First, you heat a gas inside a sealed cylinder. Think of it like igniting gasoline vapor. According to the law, as the temperature skyrockets, the pressure also skyrockets. This intense pressure forces the gas to expand, and it violently pushes a piston. That piston's motion is then harnessed to turn wheels, propellers, or generators.
And that right there, that simple act of using heat to increase the pressure of a gas to create motion, that is the fundamental process that drove the entire Industrial Revolution. It's the engine of our modern world, and it's all described by that one little equation.
So let's circle all the way back to where we began. We were facing the seemingly impossible problem of taming the chaos of invisible particles. But now we have the key.
Just look at this number for a second. It's 27 with 24 zeros after it. I mean, that is a mind-bogglingly huge number.
That is roughly the number of gas molecules you'd find in a single cubic meter of air at sea level. It would be literally impossible to track each one of those particles individually. Our biggest supercomputers couldn't even begin to try and handle it.
But here's the beautiful part. We don't have to. The ideal gas law is our ultimate shortcut. It lets us completely ignore the chaotic dance of trillions upon trillions of individual molecules, and instead just focus on their average collective properties: pressure, volume, and temperature. It finds the elegant, simple rule hidden deep inside all that impossible complexity.
This powerful idea of finding simplicity in chaos is what lets us predict and engineer and build with forces we can't even see. And it leaves us with one final thought. From economies to ecosystems, what other incredibly complex, chaotic systems in our world are just out there, waiting for us to discover their own beautifully simple predictive rules?